What is CTI? A couple of little things you've got to learn. Cooling Technology Institute. That's a standard. The standard, by the way, is now in ASHRAE 90.1 2010 and required by building code. All cooling tower manufacturers belong to this. It is just a way of stating what a ton is, what are the conditions, how do we compare one tower to the other. So if you're going to specify anything, you've got to make sure you always have this in your specifications. It is not brand specific. All brands belong to it. It's kind of like ARI or UL. It's just a standard you got to go by. And looking at that standard, they define a cooling tower ton. And the cooling tower ton as defined by CTI is different than a refrigeration ton. The refrigeration ton is 12,000 BTUs per hour. And by the way, that comes from melting a ton of ice, or 2,000 pounds of ice, in 24 hours using the heat of fusion, which is 144 BTUs per pound, divided by 24 hours. You can go check me out. It's not the weight of the machine. I like to tease people about that, because young kids coming out of school sometimes think 1,000-ton chiller weighs 1,000 tons. That's not the issue. I'm not trying to insult you. I'm just trying to have a little fun with this. But it is 12,000 BTUs per hour on the chilled water side. On the condenser side, on the cooling tower side, it's 15,000 BTUs per hour as defined by CTI. Why would it be a different number? Do you remember that heat of vaporization? Do you remember the kW we were putting into that chiller, into compressor, to raise that low pressure, low temperature gas to a high pressure, high temperature gas? That's work. That's kW that you're putting into the centrifugal or reciprocating motor. And that kW winds up in the cooling tower load. And nominally that would be 3,000 BTUs per ton, as defined by CTI. So CTI says if you buy a cooling tower that's rated for 1,000 tons, it's going to be rated at 15,000 BTUs per ton, not 12, because of the compressor. You've got to take that kW that you put in the compressor, those BTUs wind up where? Out in the cooling tower. And you have to get rid of them. They got to go back. You got to take care of them. So from now on, cooling tower is 15,000. And that's the standard CTI definition. And every cooling tower vendor will use that same number when they tell you it's certified. So we got to talk a little bit more about conditions and standard conditions for CTI. If you look at a standard condition, everybody thinks this is a standard condition, and CTI defines it as the standard condition. The range would be 85, 95. In other words, I'm going to make 85-degree water. I'm going to have 95-degree water coming back from my chillers or my condensers, and it's going to be a 10-degree range. And I'm going to do it at a 7-degree approach. I'm going to do it at 78-degree wet bulb. So here we go. Normal statement would be 85, 95, 10-degree range, 78-degree wet bulb. That's a 7-degree approach to the 85-degree condenser water I'm making. And that works out to be 3 GPM per ton with a 15,000 BTU hour ton. This is all out of ASHRAE, but there's nothing magical about it. The reason I mention ASHRAE here is because that's where you're going to go to find your conditions for Greenville, South Carolina, or LA, or Alaska. Wherever in the world you want to go, you go to ASHRAE and you look to determine what your local design wet bulb should be. And when you do that, you soon realize there's nothing magical about this nominal condition. So here we go. In our local part of the world where I live in Greensboro, the nominal is 78, and that's pretty much right out of the book. But if you were in Mobile, Alabama, it's 80 degrees wet bulb. That's right, much higher humidity. You go to Las Vegas, it's 71. Yeah, 71-degree wet bulb is designed. You know, in the summertime in Vegas, it gets 105, 110 degrees, sensible. But the lake never gets that hot. Remember, a cooling tower is designed on the wet bulb, on the latent, on the ability of the air to hold moisture, on boiling off 1 pound, 1,000 BTUs per pound evaporation rate. That's what controls how a cooling tower works. So you size towers based on the wet bulb, not the dry bulb. Size a cooling tower based on the wet bulb and not the dry bulb. And you can see out west, the wet bulb's a lot lower. So you can certainly say the cooling towers will be more effective than they already are. So Nothing magical about nominal conditions. And if you're going to design in Charleston, South Carolina, you better use 80-degree wet bulb, or you're not going to be very happy. So to work our way through this range thing, let's talk about it a little bit. We said the nominal range was 10 degrees. That would be making 85-degree condenser water with 95 going to the tower. And that was 3 GPM per ton based on 15,000 BTUs per ton. Good. What's wrong with 15-degree range? What's wrong with making 85-degree water and having 100-degree water back to the tower? It would reduce our flow rate from 3 GPM per ton down to 2 GPM per ton. As you see, nothing really wrong with it. Whatever's best for your application, best for your chiller. There's no one answer to that. But I want you to make sure you learn this one thing, and this is a real fundamental thing that you need to relate back to the refrigeration story. If you had a nominal 95 to 85-degree range, what's the midpoint? The midpoint is 90 degrees. So on average, I am condensing that refrigerant at 90 degrees. Wait a minute. Compare that to the 85 to 100. What's the average temperature? Average temperature is what? Let me figure the 92.5 degrees. So there, my average condensing temperature on the 15-degree range is 92.5 versus on the 10-degree range is 90. So in the same application, the centrifugal chiller has to work harder because the condensing temperature controls the pressure. Remember that on the refrigeration story. The temperature controls the pressure. The higher the condensing temperature, the more work the chiller's got to do. Doesn't matter. The more work it's got to do, the more kW you have on the electric bill. But wait a minute. So you're telling me in the 15-degree range delta T that my compressor is going to work hard. Yes, every compressor in the world is going to work hard. But wait a minute. I've reduced the condenser water pump flow to 2 GPM per ton versus 3, so I've got less pump horsepower. Which is best? I do not know. I can't answer that. But you've got to look at both. You've got to look at the increase in the kW to the chiller and the decrease in the pump as you look at this to determine what is best for your application. Be happy to help you with it if you want to get there, but it's important you understand those two relationships if you're going to play with towers and chillers and pumps. So how about this cooling tower approach thing? We said 85-degree water we were making with 78-degree wet bulb. 7-degree approach, nominal. What's wrong with a 5-degree approach? What's wrong with making 85-degree water with 8-degree wet bulb? Nothing. It works. Cooling tower is going to be bigger. What's wrong with 80-degree water with 74-degree wet bulb? 6-degree approach? Nothing. Cooling tower is just going to be bigger. That approach temperature, the higher it is, the smaller. The closer the approach, the bigger the tower. And it's first cost. You're talking direct control of the first cost. Again, what is best for your application is the key. So let's look at a typical cross-flow cooling tower. Double-sided, hot deck vent on the top. I got water going in the hot deck, little tiny holes, and the water just flows by natural gravity all over the field to keep that field nice and wet. I got air pulling in from the side, say 78-degree wet bulb on design, and I'm making 85-degree water at the bottom. On the cold deck, the blue part at the bottom, and the cold part, that's where the cold water basin is. So if I kind of put a few numbers to this thing to make sure you understand what approach is, by controlling that airflow going out the top, I can control my leaving water temperature and hold it at 85. On a nominal day, I'd have full capacity and tonnage, 78-degree wet bulb going in both sides. It's a double-side tower. I'd have 95-degree water going into my hot decks at the top. I'd evaporate 15 pounds per ton. Wow, throwing something new at you. Not really. I said the nominal tonnage was 15,000 BTUs per ton for a cooling tower ton. 15,000 BTUs per ton. So if we get 1,000 BTUs per pound of water, then I have to evaporate 15 pounds of water for every ton in my cooling tower. Simple little thing that you ought to hang on to. It's not exactly 15, but it's so close you can use it and go on. So you're saying to me, Chris, for every ton of load on my cooling tower, I'm going to evaporate 15 pounds of water. Absolutely. Let's keep it simple. That's exactly what you're going to do. You're going to have rocks left behind, by the way, which we'll talk about later on. But you're going to have to do that. So now I'm making 85-degree water, and what's my approach? My approach becomes 7 degrees. And that's what I want to make sure you understand. That's about all the terms I really want you to understand, but you need to kind of make sure you're comfortable with these approaches and the range and the flow rates, because you start data evaluating cooling towers, it is critical. Thanks for tuning in. Have a great day.